the top, you have the top three performers in the LLM market, the large language models, right? So you can actually, I don't know if you guys know, but you can download Llama or the Alpaca series or Contrast, and you can run them locally. You can make your own version of ChatGPT.
Really?
Yeah. Yeah. It requires quite a computer to do it. I'm not gonna lie. I've got one system that's only able to run part of a model, and it's a $20,000 computer. So, but some of these, like Code Llama and the new version of Alpaca, those are actually like you can run them. So I can verify that you can run them all on a mobile device.
Oh wow!
I saw them running the other day. So there's one student that's in Dr. Lee's lab who's been working on getting some large language models running local on small devices. So you can. We'll talk about how you do that. It's an interesting process, but we're going to only talk about some aspects of it. But it's an interesting consideration with regard to the idea of how LLMs work, right? So you have the idea of sequential modeling, and then you have the idea of likelihoods. Essentially, the likelihoods cascade together. Well, when you have all disciplines, and you have a large space of disciplines, think about it from the perspective of the cursive dimensionality starts to happen there. And think about the trade-off that we have to suffer with regard to bias and variance, right? So the variance is the capacity to work in a variety of different domains because each of those domains have their own data characteristics. The biasing aspect is how accurate you're going to be in your local scope, right? So you're going to lose accuracy in order to extend your scope. So the model will become, anytime it becomes more generalist, it becomes less accurate. So its reliability tends to drop when you try to make a broader model. So you make a narrower model that works for fewer subsets of information, you'll get better performance because of the limitations with regard to the flexibility the model has, right? If it doesn't have enough, it's like, how many equations can you memorize? And then how can you apply those equations to understanding and solving problems in the world? When you think about it from a certain perspective, we have to have a subset of equations with respect to all the ones that can be known to work with so that we're able to be an expert in the area we're in. If you go and you learn every possible system, then it's going to be very confusing as to know which one I need to use in which scenario. And so that's the big problem with some of the large scale models is that they are limited in their scope based upon the real world constraints, right? So you want to make something that's super accurate, you can't have too many different topics, and that creates issues. So many issues that I'm sure you can sort of unpack.
So is there any kind of work or anything to try to get these models to like shrink down but yet have parallelism, like be able to run parallel with other language models at the same time that are more
categorical models, right? That's where we look at it and say you have so the human brain is set up this way, simple, right? You have an overarching model, and this is sort of the director model, right? It's the executive model. So the executive model is
একটা হলেই হবে কিন্তু যেটা খুব স্ট্রং কিন্তু আবার কাপড় ছিঁড়ে না এরকম কাপড় কালার নষ্ট করে না এরকম মোলটা খুব কাজে দিছিল ঠিক আছে sorry my brother called me sorry
go outside if you need to talk. All right, so each one of these could be a separate model, right? This one up here says I was trained to do what? I was trained to identify the type of problem and determine its domain. Then I shunt the problem to the appropriate model relative to what it's good at, right? So this is the electrical engineering model, the computer science model, the mechanical engineering model, you know, the social design model, whatever it is, right? So it shunts it to the appropriate model. Now that the first decision isn't about how to solve the problem, it's just about who's best at it. So this happens in many environments, right? We have the executive space, and then we have a variety of departments. This becomes an org chart. Right? So what we end up with is these models are much smaller, in truth. Right? They're very small, and they perform better on their domain space. We haven't been able to build one of these yet. We don't know how to do it. That is a serious open challenge, like at the Millennium Problem level, right? How do I create a model that's good at determining how to solve, or at least who might be good at solving the problem, without necessarily being able to solve the problem itself?
Is that
Which
part
is
of the
weird,
test?
because we can do that. We can tell, I think you'd be good at this, I think you'd be good at this, because of some past characteristics. But how do we link that together? Without domain-specific knowledge, how are we able to access that information, right? And is the priming of some domain-specific knowledge part of how that works? Like having a rough understanding of the space allows me to be able to generalize it. I don't think that there's a rough understanding and generalization capacity yet within ML models, right? We haven't really figured out how to bridge that gap. We haven't figured out how to bridge the confidence characteristic with regard to saying, I'm an executive, I'm gonna be the CEO of the company, and I can direct people to their various groupings, okay? No shade on Elon Musk with regard to what he's accomplished in his life. But do I think Elon Musk is good at spaceships, drilling underground, building electric cars? No. Building robots now? No, he can't be good at all those things, okay? Is he good at figuring out who to hire to do the job? Absolutely.
Yeah.
Okay, so he's an executive decision model. Maybe we can model his brain, okay? We'll just Neuralink him, and we'll download it. And then we've got
Nice.
hands clean, okay? Sorry, totally atypical discussion, but something that I think is interesting with regard to, sort of a meta-analysis of what we're going to be doing here. We're building the models that are at the very bottom of the org chart, okay?
Several layers.
They're the worker bees at the very bottom of the array, okay? So these first few are just tell the difference between things, right? But at the same level, that executive is a classifier, right? It says what class of problem is this? If I select the correct class, then I can just use a routing mechanism and say, okay, select, now reroute the problem to that group. So that's technically a classifier. What we haven't figured out is how to make a classifier with adequate spatial complexity, temporal complexity to be able to work that yet. So there's limits here, and we'll see what the limits are. So we were discussing toward the end last time the idea of within logistic regression, right? So we said logistic regression was a mechanism by which we applied a alternative function to a strictly linear operation in order to be able to solve a probability-based problem rather than a strictly linear separability issue. And what do you guys remember about what the linear regressions problem was? What was linear regression's problem? Why did we get rid of it?
So
why did we say it doesn't work in all cases?
it
Tends to go through the density of the.
It does not reach. It goes below 0.
You guys are all right. All of you. You picked a part of it. Each one of you picked a part of it and said it right. Okay. You said the probabilities can exceed
Below 0.
reliable values below 0. You said that it can extrapolate past 1. Okay. Both of those are true. And then you brought in an additional characteristic, and this is one that I think is maybe missed by some people, and that is it does not work well with unfair distributions. Okay, it doesn't work well whenever we don't have equivalent numbers of samples in each class. We call this sets imbalanced, right? The scales are tipped in one direction or another. So when it's biased towards one specific class, right? We're going to use the other definition of the word bias now. We're going to use our idea of a grouping implicitly implying, implicitly characterizing the output with respect to the majority class characteristic. So let's think about it this way. I have two options available to me. And I say there are 90% of option A and 10% of option B, right? If I'm unsure, where do I put it? Option A every time, okay? So this system is one that starts off where? 50%, right? 0.5 for probabilities. Tip the scale even slightly in one direction or another, and the ball rolls that way, okay?
Right.
So 51% goes down the hill, okay? Not very fast, but okay? So the idea is even a slight imbalance will offset that distribution. What happens to that when I say the offset of the distribution? I'm talking about let's go for it. This is not a good example, but I want to talk about it real quick in a minute, all right? So we'll come back. Do you see this equation? Do we look at this one? I don't think we looked at this one yet. Okay. This is actually what we call the logistic regression function, okay, or at least the objective function of the logistic regression. It's based upon this nonlinearity, okay? It is a slight nonlinearity because of the fact that it has a linear component, but then it's applying a non-linearity to it. It's applying the natural logarithm, right? So there's a relationship, everybody understands the inverse relationship between the natural exponential and the logarithm, right? It's an inverse relationship. So we're actually taking a line, right, and we're substituting it for the value of lambda in the natural exponential. So we say the exponential raised to the line. Now, that's actually sort of a negative precept, right? It's a negative value that we're putting in there. But that's, nonetheless, that's a problem for higher math people than me. The shape that is developed as a result of this is essentially a reflected logarithmic expansion, right? So you start off with a log increase, and then you have a small logarithmic decrease, right? Reflected along a central axis. Now, we want this thing to be able to go from 0 to 1. So I say, well, I need to be able to make it work as known. How does this operate? Initially, it starts off by operating between -1 and 1, right? It's reflected over the vertical axis. The reason why is because at 0, it's halfway through its transition. Now, as it goes below 0 to low value all the way to -1, it has an asymptotic relationship towards the 0 value. And then as it goes up towards the direction of +1, it has another asymptotic relationship. Okay? It gets closer, 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 closer to 1, and then is exactly 1 at the end of its precept. All right? So depending on the tightness that you're applying to this function, will depend on sort of the slope of the output. So we have a line here. There's a line. Where's the line? We like that we have a line because we figured out how to solve the line already, right? You solve the line. If I say the objective of this function is to get the value of the probability for the output of the system to be set exactly at the 50% mark, then that's fairly easy. I can determine whether or not it's adding up to that by placing half above and half below, half on the right, half on the left, essentially. So I have this line that comes up through the space, converts, and then goes over. Okay? We have this is our transection space, right? It's now at the halfway mark. Because originally it started off, right? -1 to 1, it went up, went over, like this. We add 1 to the bottom, and it shifts it over, punches it over, okay? It's still going to have a 1, but it's going to go over at half, at 0.5, right? So unchanged, set to 0. If I set the beta naught component of this system, a bias, 0. This is the reason why we use the bias, all right? The distribution here, similar to the mean of the spatial distribution in the two-dimensional space, the distribution here is as a result of the median of the two distributions as oriented on the projected axis, right? So we have all of our zeros are down here, all of our ones are up here. We've got the means of these characteristics, these means of these distributions, and then we have sort of a spacing where we're going to place this in the middle of the means, right? Ostensibly, okay? It's based upon a couple of different characteristics. It's a weighted characteristic. Where I place the position of the halfway mark of the line. When you think about these sigmoids, they are always going to sort of cross through that central location of beta. Right? That first value coefficient is just it's a whole value, right? So it's additive. So when I say beta naught, I'm talking about the idea of, well, let's do it from this direction. If I start off at exactly 0.5 or halfway between these values, any value of beta naught, that's negative and that's positive. I move the whole thing through the probability or through the space, right? I can shift it forward. All it does is move it up. It's the same shape, but it's been moved up, right? Also, likewise, move it back, same shape, just moved back. Beta naught is just how far forward or how far back that line is with respect to the value of x. Okay? Everybody get that? Now, where's the slope characteristic? Where's beta 1? It's the steepness of a line transecting, so I'm not doing this exactly right. It's a line transecting where that sigmoid actually runs. The line in the center of that sigmoid is a line of interest, right? That's the slope. So let's change it. What happens when we change it? I'm getting too many things on one thing. All right, so let's do it down here. Let's do another one. What happens when I change the slope? So initially I have this guy goes up pretty tight, right? If I change the slope, I have this guy. Notice it's still a smooth transformation, and it's still a sigmoid, because it's approaching both ends in that smooth fashion. But now I have a little bit of play, right? What would this be an indication of with regard to what we were looking at beforehand? Let me show you something. I'm going to show you something about how our eyes work. Okay? We were able to pick this out real quick, right? We said, oh yeah, right here. Right? Look how many blue circles there are. Look how far over they go. We didn't even see that initially, right? Our brain didn't look at it. It said, oh, I'm just going to pick out the things that are different. So the red X is covered up over the blue ones in our brain, right? Because we were counting differentiation. But in reality, this is very overlapped. There's a lot of samples that are non-defaults all the way out here into this heavy default space, right? So there's quite a density of examples that indicate that there are individuals with fairly significant, up to several with $2,000 or $1,500 to $2,000 debt, even at low income rates, right? Notice, I think that's interesting because the higher you go, the lower the density of individuals in non-default in the higher earning spaces. So there's a non-linearity here. It is there. It's weird, but it's there. That the more money you make, the less money you need to borrow or likely to need to borrow, but the higher your likelihood of defaulting if you borrow past that point. So there's a complexity. We're flattening it by looking primarily at just income, or excuse me, primarily just balance rather than income. But notice here what we're dealing with. We have overlap, right? You remember here where we said income had overlap characteristic? How confident am I about the capacity to separate those two groups? How do I place a logistic regression such that it cuts those two groups in half? Well, there is a region right here in between this mean and this mean where for a brief period of time your chances might be right at the center of the balance, okay? But it's still really, really bad. So I would say my confidence, right? If I say you're past 0.5, I say you're a 1, right? If you're below 0.5, I say you're a 0. So this is an indication that the values that are in this space are getting projected to or becoming zeros, and the values in this space are projected to becoming 1s. If I'm very, very sure about it, what does it look like? Looks like a step function, right? Like I said, a step function. This is like ultimate certainty. It's cut off, right? There's no values where I say, well, it's a 0, but I'm like, I'm 37% sure it's a 0, right? I'm 18% sure that it's, like a 1, right? So it's how it's getting along that space. Now think about, one of the things about this that's interesting is this is actually only a value of membership. So when I say probability of membership, I actually don't have a probability of being 0. I have a probability of being 1, okay? So when I'm ranking this, I say if I say probability here, probability for x, what is that P of x of? P of x being equal to 1, right? P of x for class 1. So it's probability of class membership to the target number set, one versus the rest. So whenever I say a probability here, this is dimensionally locked, it doesn't say how likely it is to be a 0 or how likely it is to be a 1. It says how likely it is to be a 1, and then we determine how likely it is to be a 0 by subtracting its likelihood to be a 1. Because it either has to be a 1 or a 0. Everybody get what I'm saying by that? Okay. So it's essentially the remaining of the total probability with respect to the value. My probability that I'm assessing is only going to tell me whether I'm a 1. So I say my likelihood of being a 1 starts off fairly low down here because most of the samples that I have are zeros. However, a few samples start to show up. A few non-zeros start to show up through this space. The more non-zeros that start to show up through the space, we should see a smooth curvature, right? We should say an increasing likelihood for them to be 1s, and then plateauing with respect to the likelihood to be 1s, to a point where we become certain. This is an indication here. The amount of shift that this has is an indication essentially of the relative uncertainty or overlap with respect to the distribution. So the more overlapped they are, the more curved that line has to become. Essentially with logistic regression, the higher that beta 1 coefficient is, the less certain we are, the less separable those two classes are spatially. I'm making a grand oversimplification here, but I think it works, okay? The reason why I say that is I've talked about this quite a bit, and this is one of those things that I've recently kind of come to a conclusion on, to say that it's a metric that we can use as a rule of thumb metric. It's a heuristic, but it's not hard and fast, right? What did you want?
So, if there is no overlap, like there is a less overlap, what happens? It becomes step.
It becomes a step function, right? If we can decide an exact location relative to the cutoff point between two values, then we just put the step function in place, right? Logistic regression is actually not well suited to that. You can just use a biasing value. You can use a threshold, right? So that's essentially what the step function is a threshold function, right? It's an instantaneous shift based
Shift between.
So if I'm understanding you correctly, the balance would be a more smooth curve because they're not overlapped as much?
Balance would be more vertical.
More vertical, okay.
Yeah.
Okay.
So I say I'm more confident about where I've placed. So you can think about that as how confident I am about where I've placed that line, right?
Right.
The uncertainty it comes with if there's values over here, right, and there's values over here. Let me draw this real quick. Try to see this. So if I've got O's, right, and I've got some X's, we are going to project these up onto this axis, right? We're going to project these down onto this axis. So we're going to place our sigmoid on this surface like this, right? 1s, 0s.
Okay.
The reason why I say it's fairly vertical whenever they're easily separable is because of the fact that it's pretty obvious where the transition, where the halfway point would be for the transition, right? But imagine that I put a few X's over here and a few O's over here. Now I'm less confident, right? We go, well, there's actually a few that could be, so I'm going to have to increase the likelihood of it being potentially an X over here. The median group should stay relatively the same, so I might not have to adjust the bias a lot, but I could have to adjust the bias, right? So if the weight started back here a little bit further, I might even have to move this back a little bit in order to compensate, right? So I might have to drive through this, and then I still have to take into consideration the O's that are present now here, right? So there's a few O's that got into the X's space, so now I'm less confident about the fast transition to 100% confidence that it's always going to be an X in that space, right? So it's saying how confident am I on this side of the reflected space and how confident am I on this side of the reflected space. Keep in mind, you can't deal with those independently with this version, okay? It's reflected across whatever that bias axis is. So it's the same up here as it is up here, right? Because it's a line that essentially the axis of that line, the tilt point of that line, is that 50% mark. So the beta naught is where that 50% mark should exist. So we optimize that relative to the slide of the threshold point, and then we balance it based upon how confident we are or how much overlap exists in that space to compensate for that overlap, right? Heavy overlap is going to be pretty big. Almost no overlap is going to be virtually vertical. Matter of fact, the Heaviside step function is an operation that is applied to a sigmoid to make that square step function. Right? So that, in reality, the Heaviside step function is the Dirac delta, the impulse function of the instantaneous impulse function over the value, the bias value of the sigmoid. It doesn't exist in the natural world. Most electronics are sigmoids, right? They don't actually have they don't have step functions. Step function is ideal. In the real world, it's a polarization, right? So I'm gonna charge an inductor, or I'm gonna charge a capacitor, right? It's the rate of charge which can happen. If we compress it down and try to make it happen on one point and have a threshold value, it's the integration of the sigmoid that becomes the step function. I'm applying that for my electricals, or my mechanicals, and I've taken some of it. Okay. Let's do this real quick. Let's talk about this real quick. This works for binary, right? But does it work for anything above binary? What happens to trinary? Can I do it with trinary? No. I can't really go and draw a line here and say, all right, above this line is a 2, and this is this here, this is and there's a 1, and then this is a 0. No. Might have no.
It doesn't make it.
All right. The reason why I say this is like I can't figure out how to solve that with regard to a single space. So you remember what we did is we took. I already did this. Hold on a second. No, I didn't do it as a. Never does it work exactly like it's supposed to. Remember this problem? This is the trinary problem, right? I have 3 clusters and I have to separate them. So this is where I was talking about previously about the idea of creating a one versus the rest system. So if I use logistic regressions to reproject these, I get a similar output function to the linears, right? I can actually reproject those on a logistic space and get 3 logistic functions and create a multi-class classifier. Okay, so the difference is with how I'm projecting them, right? So here, I'm going to have some overlap between this group and this. I'm going to have some overlap between those groups, mostly those little boxes over on the right-hand side, right? So if I project onto X2, I can do a logistic regression with X2 with fairly high confidence. I can do this one, I can say, well, I'll also do X2, but this one requires me to project onto X1 to have maximal separability, right? So you have multiple different directions, multiple different values that you can take one versus the rest in order to develop your logistic regression. Which axis you're sort of flattening the projection onto for your likelihood assessment is going to matter based upon the highest efficiency of separability. We'll utilize another method later on to talk about the separability. Matter of fact, it's probably coming up pretty quick here. All right? So you can't really utilize logistic regression. Well, actually, multi-class logistic regression is the utility there, right? That's the MP logistic. That's where I do one versus the rest, but instead of doing linear classifiers or linear regressions to get the classifiers for the multispatial, I do it with the logistic outputs. They tend to perform just slightly better than the linears. Okay, overall, it performs slightly better than linears. It depends on the degree of overlap, right? The separability of the model, and we'll look at a couple of like axiomatics where we say in general this is the case. But we tend to utilize when we need most cases, like linear regression is not appropriate, but discriminant analysis might actually be a little better here. And we'll talk about what discriminant analysis is. So we talked about the logistic regression, and if we use a reorganization, so we take this original equation, like I said, this one's really easy. The bottom portion is the shift to make it where it's valid only from 0 to 1. And then you have 2 versions of the same linearity, right? The bottom portion indicates an identity version of the matrix. that is saying that there is a logistic for every one of the classes, right? So you have the class target, you have all classes, and then you have the shift in order to be able to bring it in place. So we're gonna get the probability of being the target class for x, right? Given the value of x for the vector, relative to all the classes based upon one value. So this says this P of x only tells you the likelihood of it being a member of y equaling 1, right, the first class. If I do a multi-logistic regression, I'm going to have one that says likelihood of being class 1, likelihood of being class 2, likelihood of being class 3, okay? Those do not have to add up to 1. That is not a total probability system. That is saying a membership likelihood relationship is one at a time, right? The only likelihood that has to add up to 1 is the likelihood of it being either in or out, not the likelihood of multiple membership. So you can have a 68% chance of being in class 1 and a 53% chance of being in class 2. Okay? Which one you take? You just take whichever one is higher. Take whichever one is higher. We're going to rank these and we're to say that the value output is whichever one's higher. So we call this function, this version of the function, this linearity is actually the logistic regression, and it's a monotonic transform based upon the log or logit scale. So this is the log of the probability of value x at over 1 minus the probability of membership, right? So it's just the log in both scales, plus and minus. That's going from and going to. All right. That's the same thing. All right, so we talked about this and we say maximum, that's what I was describing here. Maximum log likelihood estimate is derived by this parameterization of this is just a little stylized L, and we say that that is actually the likelihood outcome for membership. We say that we have some beta non and some beta coefficient. We can generalize this as the cumulative product of all the likelihoods and all the cumulative product of the non-likelihoods. Right? It's 1 minus all the likelihoods and all the likelihoods for inclusion. So the Q product for all the groups it could be in and all the groups it is not in. So this is I described it better earlier. Right? I described it better earlier in saying that we have ultimately one log that's going to say whichever one has the highest likelihood of total membership. So this function takes the product of all of those different likelihoods and combines them together into one value that tells you the likelihood of membership to that class relative to a specific logistic regression value, so a specific bias term and a specific coefficient, right? We can maximize this. We say that if I give you a label and I give you an element, that I'm going to take the max likelihood value, and that's going to be my objective function here. I'm going to say that I want to maximize the classifier's capacity to place you in the correct grouping. Why would I do that rather than minimizing some type of error? Errors are whole values here, all right? You're either in or you're out. So when I attempt to minimize that error, whole values become very difficult. However, if I attempt to maximize the total number of individuals, then I take away that ambiguity that can be involved in the scoring process. Yes?
What does the Z statistic represent here? Is that something we've seen before?
No, don't worry about it for the moment.
Oh, okay. Is that similar to the F statistic that prints out on R when you
Yes.
do? Okay.
Yes, it is.
So just disregard it for now.
Z statistic is going to be the multi-class version of the F statistic. It's
Okay.
likelihood involvement for a specific class membership.
Okay.
So honestly, we don't do anything with that. I don't really know what's on the slide. I've had people ask that in the past, and there's a couple of guys. The guys that wrote this book, there's like 3 people that wrote this book that are core. One of them is a statistician. Like he doesn't really do much in terms of actual like computational mathematics. So he likes to throw in these weird things. I don't know if you've ever watched the videos, but there's two of them, old stodgy East Coast white guys, right? They're sitting there talking, and then the one guy with the slightly longer hair will go off on something, and then the other guy will like be like, hold on, and they'll like stop him and be like, let's get back on target, you know? He's always off on a tangent. So this is like a tangent moment.
Okay.
We know what the coefficient is. We know what the relative standard error is, and then we know what the p-value is. You could acknowledge this as something related to the t-score, but we know what p-value. Since we know that p-value has an indication of high statistical significance, then we know that it's likely a good intercept value. However, this z statistic characterizes in saying that I need an offset, right? So the offset here is related to the value of the coefficient, right? It's the quality of this offset relative to the quality of this slope of the overlap, okay? So the standard error relative to the offset, what is this? This is the intercept, is where I'm placing the value of the midpoint. So it's saying there's a lot of error, a lot of the standard error appears to be incurred by having a less than ideal distribution around that offset. There's fairly high error because of variance due to overlap, right? So the variance is each class bleeds into one another. So the bleeding, the more it bleeds, the worse that contribution of the offset is going to be to the total error in the system. So yes, it's fairly, the coefficient for balance is pretty low, but it's because we're dealing with whole numbers, right? These are it's non-normalized. It's thousands of dollars, right? So when you have thousands of dollars, you're going to end up with a fairly seemingly low slope, right? But if you categorize that according to a big long line, you see a tiny little increase, right? But if we compress it where we look at it, it seems pretty tight and pretty steep, okay? So along one axis is like tens of thousands of dollars. Along the other axis is thousands of dollars. Okay, so we graph this, it's going to look weird in comparison or characteristic to this tiny value. This says relative to every dollar that you bring out over whatever this offset coefficient is for tens of thousands to thousands of dollars, right? So this is a ratio of 10. So it says if you make the 17 grand or whatever, you borrow the 1,750. But for every dollar you borrow, your likelihood of going into default increases by a value of 1/2 of 1%, right? That's every single buck that you borrow increases 1/2 of 1% of your likelihood of default. All the way up into a point where you say you're going to default out of it. Okay, so for multiple classes, from a strict class state estimate, this utilizes the GLM function in R. GLM is the G is used as a functional characteristic. It says G and then it is LM, logistic, right? So G is going to be your G modeler for logistic operation. Okay. We talked about where we actually get these values from, right? And what we do is we plug these into our estimators. We use the coefficients we calculated, and then the output is going to be your likelihood of default, right? So likelihood of default at $1,000, %-ish. Likelihood at $2,000 is about 58%, okay? So it shows that it's a pretty quick transition between the $1,000 and $2,000 mark, right? To increase pretty quickly. So it's increasing pretty quickly at the $1,000, $2,000 mark, all right? We'll talk about adding in the student as a predictor next time, and we'll also talk about the idea of utilizing an alternative mechanism. Hold on, let's see if I can find it. Called discriminant analysis, which utilizes a flip, right? We flip things around by assumption of a Bayesian discriminant, right? So I'll upload some stuff on Bayes. It's gonna be similar to what you've already seen, but I'll upload some stuff on Bayes. A couple of ideas around it, get us familiarized with it again. I know you've seen it in like basic stats classes, but you may not have worked with it a lot. But linear discriminant analysis is a really cool tool that allows us to remap the way this system works, and we can solve problems by combination, okay? So the linear discriminant method allows us to map the likelihood, or the characteristic of likelihood, based upon the clustering relative to the direction that we're projecting the values onto. mentioning beforehand that whenever we were looking at the values of red versus the rest, it was easier to project onto X1, whereas the remainder is projected onto X2, right? Notice the overlap in this direction is high, but the overlap in this direction is not. So the linear discriminant analysis actually allows us to rotate the data, which, right, any rotation is actually just a transform. So we can rotate the data until we get the angle that we like, that has the maximum separability between the classes in order to be able to derive our localized version of the regression. And instead of having to stick with a logistic, we can just use a linear offset by setting the values wherever the values are equal in terms of their likelihoods of membership, okay? So look forward to that. I think that's one of the more fun things we do with regard to classification, okay? So next week, we'll start off on that, and I'm gonna be adding a lab for this, so be on the lookout for the lab for this section. I think the labs are really good, because I think that they concrete in your head how this stuff actually works. I will probably be handing you guys some actual data sets to work with that I prefer with regard to classification, rather than letting you guys just run free in the wild like I did with this last one. Okay? I wanted you to run free and see what was out there, but at the same time, now I need to curate a little bit so you get outcomes that you feel comfortable with. Because if you throw something at you, say classify this other thing, whether somebody was hiring out and they were thinking, you know, that might be a little much, all right, a little much. That might be difficult to differentiate. Lots of potential overlap there. Okay? So, thank you guys. Have a good weekend. Appreciate all being here. Thank you. Thank you.
Professor, I had a quick question.
Sure.
So I know we're looking at having our first applied probability test this coming Thursday.
Correct.
And you said we're allowed to make a one-page note card?
I haven't cut out, but I will. You're right, I forgot.
And
What I'm looking for is, I'm trying to determine for this first exam whether I want to do a full sheet or half sheets. And I
Okay.
actually might just give you the first one.
Oh,
Yeah, because the reason why is we don't have a ton of formulas, and I can relatively easily put together most of the formulas we're working with. So I can like make a list of all your axes, make a list of all your ratios, make a list of like multiplicative unions, intersections, draw some maps there for you, and just give you guys like a half sheet of that for reference. So I know some students are not gonna. What I should do is I should do it in advance, hand it to you so you know what's on there, and then you can crib from that and add it. So you can either use the one that I'm giving you as a reference, or you can make your own.
Could
But I would
we
stick with
imitate the one that you give us?
That's
A little
fine.
bit with
That's
like,
fine. That's what I'm
N
thinking.
is the number of blah, blah,
Yeah.
blah, and R is.
I'm thinking to do that. That's what usually. By the time you write it down, you won't need it. You won't need it. That's the part that always makes sense to me. Is like, yeah,
I hate having
N
to
and
write
M.
my own,
yeah.
but in the same time, I think it's a good tool, you
Yeah.
guys letting us do that, because it forces us to go back and study again. At least for me, it did, but writing out the functions helps reinforce in my brain what it is I'm doing.
That's a fair point. And
Now,
that's-
if you wanted to
No, I
get
think
more
you're
and
right.
I just write it out off of there, that's a good idea, because a lot of it, there is a lot of overlap, I think, in this first section, and
What I'm really concerned with is people bringing in a single-sided or double-sided 8.5 by 11 with a bunch of tiny printed out versions of the problems, and thinking that they're going to just be able
well,
to.
you already said not to do that, so.
I said not to do that, but that does not stop people, and it does not stop large chunks of the students from doing it, and it becomes problematic
Right.
whenever you sort of have this like consolidated force of students going to do what students going to do, and then like, well, can I punish all 20 of you that did this? This is dumb. Typically, I don't have as much problem with the undergraduate as I do with the graduate group. I don't know why graduate seems like they should be more behaved, but they don't. Right? I had the worst time I've ever had over the summer with people literally bringing in like verbatim copies of my responses to a key from the previous semester.
Wow.
Right, and then they wrote my answer verbatim on the exam to a question that I had changed.
That's
I made
plagiarism
a
though,
change
if
to
they
the
haven't
question.
already taken.
It's a violation of academic integrity, and I gave them a warning for it. So, and that's pretty strict. It's pretty strict. Like I actually I told them one more hiccup in there and I was reporting.
Well, the way Mr. Beard did, Dr. Beard did it was, he said we could put down examples, but not actual problems. Like, he didn't want, like, I didn't put down any physical problems,
See, they're
but I
generic.
left the variable.
There are generic worked versions of these problems, like generic, like the high level ones, in that supplemental textbook that I gave you guys,
Mhm.
right? There's fewer work problems that I think even really apply. I don't know, that book is weird, right? I like it because if you're really mathy, it's a great resource.
Right.
The work problems down below often are missing some of the pieces of some of the things we do, and you have to kind of find them throughout places. But I like it because if you wanted to go and make a version of like how to work this problem, you can find the generic, like global, like this is the equation. Really mathy, really like variable latent, but if you know what that means, you can just plug the values into it and solve it. I'm fine with that. Fine with that. My question is whether I want to give you guys one full single-sided 8.5 by 11, or whether I want to do half sheet. I think the only thing that happens when I do half sheet is the students that want to bring in a magnifying glass or a microscope can get just as much crap on it as they can on an 8.5.
You'd be surprised how much I can fit on a half sheet
Oh,
of
don't
paper.
even get me started. There was a girl in my cohort.
I can write
where I was
really
taking
small.
some stuff. I'm saying I could not read her writing. It was too small. She used a 003 lead to write.
They even make that in the
Yes,
that.
yes. It's they call it microfine. And I can't write with it because I break it.
Oh,
she had
yeah.
tiny little delicate hands, and she could. I mean, I'm telling you, she was,
0.5 is the smallest I can get.
it was stupid. It was stupid how much stuff she could fit on an 8.5 by, or a 3 by 5 card.
Honestly, I mean, that's another thing Dr.
I had
Beard
one.
did.
She
He
gave me one
limited
of them,
it
and I
to
had
a
it
half.
laminated.
Because he said if I give you a full sheet, which I've done, people put too much on there and then they're not trying to do the test. They're trying to find what's gonna give them the solution to the test.
Overfitting.
And you know,
Yeah,
that's
yeah.
why, well, and Dr. Kirkpatrick, he gave us a front and a back for control systems.
He did.
Front and back, 8.5 by 11. That was almost too much, even for me, because overfitting. Like,
Then you're more worried about trying to make sure everything's on your sheet more than you are trying to figure out how to review the material.
well, and then did you do it in a logical process? Like, that's one of the first things I sit down and do. Like, am I going column or am I going like this?
So what we used to do is we used to take full 8.5 by 11s. We would quarter them. We
Okay.
quarter them, and then you do a section a quarter, right? And then we actually got to a point where I would scan them in and I'd put them in Photoshop and I would like move stuff around, like if I needed to rearrange it, I'd do that.
Well,
But
that's-
you should see our note of what the three guys that I had in my PhD lab with me. When we did our qualifying exam, you got 5 full double-sided 8.5 by 11 sheets. Okay, your qualifying exam is everything, literally anything that has been in your entirety of your undergraduate and graduate courses can be included.
Really?
Yes.
But you have to decide what the importance is and what to put
You
on.
got a piece of paper, figure it out, put it on there.
Wow, man,
Wages,
can you put an entire
concepts,
undergrad on one piece of paper?
I can put entire topics on one piece of paper, yeah, I have them, I have all my notes, if you're ever interested to see them. We put, all three of us put together and we had our consolidated note page.
Yeah, we're not allowed to Photoshop. All my professors have made them be handwritten. And
Listen,
they
I don't
verify
care
that
if you Photoshop it.
because they
If
don't
you
want us to shrink
handwrote
it down.
Okay, no, I don't care. You can write small. What I'm saying is,
Right.
the reason behind not photoshopping, part of it, the reason behind saying I like to have you handwrite it for verifiable, is I honestly don't want you to do what we did. And that's the sad part about that, right? Do as I say, not as I do.
Right.
When you get notes from somebody else, right? If it's just I got really smart bookish girls' notes, right? I don't know why, but the girls are good at making notes. Like that.
They
Number
have
one, they have
pretty-
clean handwriting. Clean handwriting. And something about the way their brain organizes information is just it's logical. We get it.
It's the highlighters too.
They use highlight, use multiple pens.
Oh, yeah. I can do
Colored
that.
pens, okay, like colored pens are so cool. Like some people that I work with, like my best note takers usually are people that use like colored pens and have like a stack of highlighters and that kind of thing. And I've seen them all over the place. But the idea is I get it from somebody else. I don't actually know, unless I'm using it actively during the process of the homework, I don't know where everything is on it. I haven't learned to be intuitive about space. That's when you see the student flipping their note card back and forth, and you go, you didn't write that. I know you didn't write it, because if you know if what you're looking for is on there.
Right.
Right, so that's where I say, I think I agree with you. Honestly, and my initial feeling was I'm gonna hand you notes, but at the same time, I think it's better that I mandate that they be handwritten. And I think I will restrict this first one to half page. So, just because of the fact that I think you need to be able to think about staying focused rather than trying to write everything, every piece of notes we take for the whole semester onto an 8.5, so.
And this may seem arbitrary, but how many questions do you think will be on it?
And that is arbitrary, I have no idea. Sometimes I do sub-questions for a header question, like just like the homework, like there may be 5 for one sub-question. So it depends on whether you ask it that way, right? How many questions versus how many subheadings are you gonna have to do calculations for? I don't know. Like usually it's 5 to 7 questions,
Okay.
but there's like, some of them will have 3 subs, some will have 5 subs. Some of them are sections with regard to like wording, verbiage, right? And the first few, like the first page is gonna be like 10 items that are all gonna be part of one question, because it's gonna be set notation characteristics.
Okay.
So set notation is like simple. Can you count? You know the concept. Can
So
you
is that
see
gonna be
the
about
circle?
half, like
Yeah, it's
first
half, rough
homework
half.
and then second homework, like
Correct,
second?
half and half.
Okay.
Yeah.
Okay, that
And it's
does
just
more
gonna be
to,
conditional probability and generalized expectation, but not a ton of specialized characteristics with regard to expectation,
Okay.
right? I don't think we're gonna do variance on the exam. I think we'll push that to the next one, so.
I just feel like I'm
I
always
don't
at the
feel like-
mercy of the
I don't
professor
feel like,
on
I
exams.
thought about what happened yesterday. With regard to answering the question on variance. And I thought about it afterwards, and I was like, anybody that's getting tied up in the exact calculation is getting tied up in the minutia. I know they want to figure out how to get the right numerical answer,
Right.
but the idea is, let's characterize it, right? The idea, the concept is the most important, because you're gonna have to figure out how to calculate it. And what we did it right afterwards, say, okay, it's easy. You multiply the potential value by its likelihood, and then you get the expected value. It's just an average of the number that have occurred within that space. It's the arithmetic mean of the whole system. And so people go, well, how do you calculate it? It's like, you freaking don't know how to calculate an arithmetic mean, right? How did you get here? This is the statistics class before this.
Oh, well, see, you keep bringing that up, but
I know.
the last time I took statistics was 25 years ago.
I see so many-
And we did nothing in my degree
You're
up to
not-
this point.
You're not in my, okay, so let me say this.
Sure.
I was laughing last night. For all the people that are sitting there and just look bored out of their mind. Like, oh God, so boring. And then afterwards, I show them something, I work it on the board, and they go, where'd you get that value? And it's like, I thought you were bored. I thought this stuff was easy. You got it. It's a cinch. Like, there's a reason why I'm going through it at the elementary level that we're going through it at. People are going, I'm getting bored.
I
But
greatly
then
appreciate it.
this last lecture, I think people got a little bit of whiplash because of the fact that I started bringing out stuff in a little bit of higher speed fashion. And it's like, we better get our running shoes on because we've got a lot of material to cover.
Right.
The basics are done. We're gonna start doing stuff with, like discretized representations and standardized distributions, calculating values. You're gonna start to need to use some summational notation. Then within a matter of like 4 weeks from now, 4 weeks from now, we're gonna be on to the calculus, right? So the last half of the class is calculus. So we have to figure out how to get up to that quick. So, but if I make it too heavy to begin with, everybody panics. And the moment I announce it at the test, the sky is falling. And it's like, I've gotten 20 emails in the last 10 hours. It's stupid.
I don't know what their deal is. I like to know well in advance because I'm a non-traditional student with 3 kids, and I have to plan
I always give you at least
so good at planning time and time management at this point in my life after going through school, like.
I will actually tell you guys what the remainder of the, when we get done with this test, we're gonna cover we're gonna do a thing where we're gonna talk about what the remainder of the class contains. We're gonna do one overview look, and then I'll tell you what the rough spots are for where the tests are gonna be for the rest of the semester.
That would be
Because I've
nice.
already got that. I've already got where the tests are gonna be and where the homeworks are. And me and my TA sit down and we refloat the whole rest of the semester to figure it out.
Personally, I
We're
wish
good time for stuff.
every class would do what we did in semiconductors and devices and microelectronics, where we had a test every week.
That all goalie?
No, that was Dr. Hanif.
Okay.
He's no longer here, but the course, even
I
before
think
Dr.
he-
Hanif
yeah,
took it
yeah.
over, you have a test every week.
He's an industry
That's
guy,
like
isn't he?
3 to 4, well, I don't know, he's no
Yeah.
longer here. Ramen's an industry guy. But it would have 3 to 4 problems on it, but it allowed you to reflect immediately on whether you were getting the concepts and everything, rather than, I don't know, but each their own. I don't ever plan on teaching, because I don't envy you guys, your position at all. I have a hard enough time trying to raise 3 kids, and I think I've
It's not
found
like
that
raising children though.
teaching
The fact
is
that I can,
not-
it's more like running a daycare than it is like.
That sounds even worse than trying to have.
It's great because you can send them home at the end of the day.
Right,
That's the
right,
difference between
right.
teaching and like raising a child and teaching a child. Raising a child is like little tiny footsteps upstairs. Like it never ends, right? Daycare is,
Oh, so it's like being grandparents, sort of.
Exactly,
You get to,
exactly.
you get to interact with them,
Yeah.
you get to help them
Yeah.
develop, and then you, oh, here's
I
some
see-
sugar,
I
and
see
go home to
teaching
your
remote.
That's the
parents.
problem, they don't give you sugar, they give you homework, so when they go home, they cry to their parents.